Assalamualaikum students, today we will do our numericals problem of chapter number 6 fluid dynamics, the numerical number 1 of your chapter 6.1. The statement of the numerical problem at your textbook is as certain globular protein particle has a density of 1246 kilogram per meter cube. It falls through pure water of coefficient of viscosity eta given as 8.0 10 raised to the power minus 4 Newton per meter square second with the terminal velocity of 3.0 centimeter per hour. Find the radius of the particle. I repeat the statement. Certain globular protein particle has a density of 1246 kilogram per meter cube. It falls through a pure water of coefficient of viscosity 8.0 10 raised to the power minus 4 Newton per meter square second with the terminal velocity of 3.0 centimeters per hour. Find the radius of the particle. Students, हमारे पास स्टेटमेंट दी गई है, हमारे पास ग्लोबुलर प्रोटीन है, उसकी डेंसिटी दी गई है, उसके अलावा कोएफिशिएंट ऑफ विस्कोसिटी ऑफ वाटर दिया गया है और उसकी टर्मिनल वेलोसिटी दी गई है और हमने क्या करना है, रेडियस फाइंड आउट करना है उस ग्लोबुलर प्रोटीन particle which we consider as a sphere. So the solution of this question can be written as solution of this question can be written as first we will write given that. What is given that? First we will write the given that, then the data. Given data, we have given density of protein molecule or protein which we mention as rho 1246 kilogram per meter cube. Student, actually at your book the statement the density of this should be 1.24 for the exact answer which is mentioned at your book. So for this sake we have to write down the density 1.246. So amend this situation, amend this problem or make a amendment of the density of protein at your book which is wrong, which is given, which should be 1.246 kilogram per meter cube. So viscosity eta 8.0 10 raised to the power minus 4 Newton per meter square second, and the terminal velocity Vt is given as 3 centimeter per hour. We will have to change this centimeter to meter per second. For this sake we will divide the 3 by 100 to convert centimeter to meter, and also divide by hours to make it second. 60 multiplied by 60, 3600. So it will be 8 10 raised to the power minus 6 meter per second. When we convert the 3 centimeter per hour to meter per second, then we will have 8 into 10 raised to the power minus 6 meter per second. What will we have to find out? To find what will we have to find out? We will have to find out the radius which we will mention as small r. Students, here are the information given as your statement of numerical problem 6.1. His given data is density of protein as nominated as rho 1.246, which is wrong, written at or typed at your textbook, which is 1246. It should be 1.246 if you want to find out the correct answer according to your book. So make it changes. Viscosity coefficient of viscosity eta given at 8.0 × 4 Newton per meter square second, and the terminal velocity is given at 3 centimeter per hour. We will have to change this centimeter into meter per second, centimeter per hour too. So for this sake, what will we have to do? We will have to do that. We will have to divide by 300 and 3600. So then we will get 8 into 10 raised to the power minus 6 meter per second. So next, what's going on? We have to find out radius of this globular protein, and the formula to solve this is formula. To solve this numerical problem, I'm going to write the formula to solve this. Students, we have read about the terminal velocity. We have derived the relation of the terminal velocity in our chapter 6, which is given as terminal velocity Vt to g gravitational acceleration r square rho over 9 eta. So rearrange this equation to find out the r, which is radius of the sphere. So by rearranging, we will have Vt multiplied by 9 eta divided by 2g and rho. Now taking the square root on both sides, then we will have r, which is radius. Now substitute the values. Vt terminal velocity 8 10 raised to the power minus 6 multiplied by 9 multiplied by coefficient of viscosity 8 into 10 raised to the power minus 6. It is also minus 6. No, it's minus 4. And divided by 2 gravitational acceleration 9.8 meter per second square, and the density of the globular protein is 1.246, and taking the root over it. Students, when we solve this, when we multiply denominators and multiply numerators and denominators, and when we solve the ratio of, then we will have r equal 4.86 after taking root and approximate this value. We will have 5 into 10 raised to the power minus 5 meter. So this is your answer. This is your answer. And if you want to if you will not change this, if you want to write the 1246 instead of this 1246, then we will have the answer like 1.6 10 raised to the power, which is mentioned at your book as 1.6 10 raised to the power minus 6 meter. So you can also change. Students, keep in mind the value of the density may be 1.246 or maybe 1246. So in both cases you can find out the answer. The first basic principle is that you will have the command on your formula, which formula can be implemented in this numerical, how can we solve this numerical, and what is the formula, and the answer is not mentioned, is not you can say that the answer is not have importance, but the calculations and the all the formulae have importance in your board exam. So the answer, the marking scheme according to is that if you write the correct formula and you put the correct values, the answer might be weightage of the marks as 0.5 or 1. So it's, I think so it's 0.5. So you can solve this question in those two cases. If you take the density as 1.246, then your answer is 5 into 10 raised to the minus 5 meter per meter. 10 raised to the minus 5 meter, and if you take 1246, then your answer will be 1.6 10 raised to the minus 6 meter, which is mentioned at your book. In the old books it should be 5 into 10 raised to the minus 5 meter. So this is the solution of this numerical. Dear learners, now we are going to solve your next numerical problem of chapter number 6, which is 6.2. The statement of this numerical problem at your textbook is as: water flows through a hose whose internal diameter is 1 centimeter at a speed of 1 meter per second. What should be the diameter of the nozzle if the water is immersed at 21 meter per second. I will repeat. Water flows through a hose whose internal diameter is 1 centimeter at a speed of 1 meter per second. What should be the diameter of the nozzle if the water is immersed at 21 meter per second? Students, we have a hose pipe like this. Consider this is a hose pipe. The white portion, neglect the red behind portion, the rear portion of this marker. Suppose that this is a pipe, okay, and there is a nozzle at the other end of the pipe, and when the water flows through inside the pipe, okay, the hose diameter, consider the diameter of this pipe is 1 centimeter, and there is a nozzle attached at the other end, and when this water eject through this nozzle, the velocity becomes 1 meter per second to 21 meter per second, because the nozzle used to throw the water, to sprinkle water fastly or through large range, or the nozzle should have very narrow diameter. So we will have to find out the diameter of that nozzle which is which is attached that hose pipe or this pipe. So let's solve this numerical problem. First of all, to solve this problem solution, we will write the given data as internal diameter of hose pipe, which we can assigned as D1, which is given as 1 centimeter. And students, you know, you are aware 1 centimeter contain 1/100 meter, so it can be written as 10⁻⁻2 meter. And speed of water hose, inside hose pipe or hose, you can write whatever, V1 equals 1 meter per second. Speed of emerging water, speed of emerging water we can write as V2 21 meter per second, which is given data of your numerical problem. What will we have to find out? What will we have to find out? We will have to find out we have to find out diameter of the nozzle. Diameter of the nozzle, which can be written as D2, because we have already mentioned the first diameter of the hose pipe as D1. Students, here we will have to find out the diameter of the nozzle which is used to sprinkle or to sprinkle the water. So formula to solve this question: equation of continuity, A1 V1 equal A2 V2. So according to the situation of numerical given data, we can use the equation of continuity, which is we have taught about in chapter number 6, A1 V1, and we will replace the area as pi R1 square into V1, and on the other side we can also write pi R2 square into V2. So students, here is pi are same, we can cancel out the pi by pi. Now we'll have, and you know very well that the radius of a sphere or radius of a round body or a circular body equal to the half of the diameter. So we can replace the radius by diameter, half of the diameter. It should be like that, D1 over 2 whole square V1, and the other side we can write as D2 over 2 whole square into V2. So students, here we will have to find out the D2. Now opening the squares, it should be D1 squares over 4 into V1 equal D2 square over 4 into V2. Now 4 we can cancel out 4 on both sides because these are same quantities, constant numbers. Now we will have only D1 square V1 equal D2 square V2. Students, here we will have to find out, we are inquired to find out the D2, which is the diameter of the nozzle. So by rearranging this equation, we will have D2 square equals this quantity, which is the velocity of the emerging water V2, will be the denominator of the D1 square over V2. So students, by taking the root on both sides, this root cancel by square, and D2 is given as D1 square V1 over V2. V1 over V2. So students, we will use this formula to solve this numerical problem. I'm going to erase it because hope you have noted down all the information. Now we will use this formula to find out the diameter of the nozzle. So by substituting the values, we will have what? Diameter is given as, first diameter is 10 to the power 2 square multiplied by V1 is 1 meter per second, V2 is given as 21 meter per second. Now by solving this, it should be 10 to the minus 4 over 21, and when we will solve this, we will have 1 over 500 meter. Now change this meter because our given first diameter of the water hose is in centimeter, so we will have to change this meter into centimeter by multiplying 100. It will convert into centimeters. Now this should be 0.2 centimeter. So student, this is the right answer, which is also at your textbook. How can we solve this numerical problem? We will use the equation of continuity, and by rearranging and solving the numerical, we can solve this numerical problem, and we can find out the numerical value. So this is yours 6.2. Dear learners, our next numerical problem of chapter number 6, which is fluid dynamics, is 6.3. 6.3. The statement of this question, numerical problem, is as the pipe near the lower end of a large water storage tank develops a small leak and a stream of water shoots from it. The top of water in tank is 15 meter above the point of leak. A. With what speed does the water rush from the hole? B. If the hole has an area of 0.060 centimeter square, how much water flow out in 1 second? I will repeat the statement. The pipe near the lower end of a large storage tank develops a small leak and a stream of water shoots from it. The top of water in tank is 15 meter above the point of leak. With what speed does the water rush from the hole? This is A, and what is B? B is that if the hole has an area of 0.60 centimeter square, how much water flows out in 1 second? Students, to solve this numerical problem, we will write the given data as height of the water, (15 meter). above the leak point or leakage point, whatever you want to write here, leak point, and area of hole or leak point or nozzle, whatever. Here the area is given as a hole, area of hole or leak point. You can write leak point, leak is given as, we should write it as a 0.060 centimeter square. To convert this centimeter into meter, we will divide it by 100 square. This should be meter square, and area become 6 into 10 raised to power minus 6 meter square. What will we have to find? There are two number A to find. What will we have to find? So what will we have to find? We will have to find A, speed, V, which is speed of water, and B, volume, rate of flow of water. Volume of water flow per second. This can be written as V capital. So students, here we'll have to find out the two things. Number one is the speed of water, emerging water, or speed does what rush out from the hole, emerging speed of water, and the other thing is the volume of the water flow rate per second. These two quantities we will have to find out. So now solve this formula. For first, to solve the first point, we will use the formula as V equals 2GH. This is the formula we have driven out in our lecture in this chapter. So we will use this formula to find out the speed of emerging water. We know that 2 is constant, G is gravitational acceleration, 9.8 meter per second square, and height is given as 15 meter. So when we solve this, we will have 17 meter per second. So this is the speed of emerging water from the hole. Student, here this is the speed of the emerging water from the hole. This is the point A. We will have to solve point B. Hope you have noted down this. Now we are going to find out solution for B statement, which is the volume of water flow per second. For this sake, we know that we can write as the formula from the equation of continuity, volume into, we know that what A1 V1 equal to A2 V2 is equal to constant, which is the volume flow per second, volume flow of liquid or fluid per second, which is equal to A1 V1 equal to A2 V2. We can write as AV according to the equation of continuity. So first we will find out the volume, then we will find out the flow per second for this area. So by substituting the values, volume, area is given as 6 into 10 raised to power minus 6 meter square, and V we have find out recently as 17 meter per second. By solving this, we will have volume as 102 10 raised to power minus 6 meter cube. Now change this meter cube into centimeter cube. We will have to multiply by, to convert this meter cube into centimeter cube, we will have multiply by this 100 cube, because 1 meter contain 100 centimeter, so this will be like this. We will have to multiply the meter by 100 centimeter, then this meter cube convert into centimeter cube. Now solving this, we will have 102 centimeters cube. So student, this is the volume. Now we are going to find out the rate of flow per unit volume of emerging water. Rate of flow per unit volume, I'm going to solve on the other side. Rate of flow, which is should be, simply we will multiply, this is the actually rate of flow, no, this is actually rate of flow in centimeter cube, we can mention as the rate of flow. So students, this is the rate of flow of the emerging water from the hole. Looking disgusted now. 102. This is the rate of flow per unit volume of emerging water. Now hope you will have understand this, and you will note down this